Hey everyone! Today we're diving into the fantastic world of artificial intelligence with data warehouse systems. While the concepts are somewhat technology agnostic, we'll be using the Google Cloud Platform to illustrate 5 key data warehousing AI patterns. So let's begin our journey by setting up our dataset and a few tables of synthetic data. This will form a foundation for our AI work. We're in a brand new Google Cloud project and can conveniently create a dataset right here in the console. One of the simplest hacks to load data is by using this nifty tool, the Cloud Shell. It's a development environment armed with convenient CLIs and effortless authentication. Plus, we'll be loading data with Python, making the editor feature a great ally for us. No need to type along, just check the video description for all the demonstrated code. Let's set the stage using a sales data example and create an orders table. With just a smattering of Python, we've got it up and running. We're cooking up random data to match the schema of order ID, customer ID, order date, amount, and status. We're leveraging a handy pandas data frame, then filling the table from that data frame. Let's get both the pandas and the Google Cloud BigQuery modules. Glancing at the console, it looks like our table is all set and the data is successfully injected. Let's take a sneak peek at this fresh table. Fantastic, looks spot on. We'll now whip up a table of products using the same formula of generating random data and slotting it into a new table. Here we deal with product IDs, names, prices, categories, and quantities. Eyeing the new table, we're doing great. Next up, the creation of a sales table uniting our orders and products. Like putting together a puzzle, we add a couple more pieces and voila! Our final puzzle piece? The product reviews table. It's somewhat of a déjà vu moment since we're using the same method of generating random data and loading it into BigQuery. However, notice how the lorem library is employed for larger chunks of text for our reviews. It's just your run-of-the-mill filler text, but lengthier than typical random strings, making it more meaningful. If you glance over here, we have some random Latin. We'll perform some intriguing processing on this data soon. Note that we've loaded more data than we need, but wanted to provide some additional foundation for you to join, process, and further enrich the data and AI in your own experimentation. Let's close up our Cloud Shell for now. The first sprinkle of artificial intelligence magic with data warehouses is through the use of remote functions. When leveraging data in our data warehouse, we can craftily incorporate AI APIs directly into our SQL. For example, fancy a bit of AI that does a translation of this Latin text? This will be a nice example of using specialized AI APIs, like for translation, sentiment analysis, or recommendation in our data transformation work. Cloud Functions will be our tool of choice for integrating with the Google Translate API. It allows us the flexibility to draft logic using the full power of a programming language. We can code away in Python, JavaScript, Go, or a myriad of other popular languages. If you're in a new project, before we get going, make sure you've got the Translation API enabled. Just search for it and activate. We'll stick to the second generation of cloud functions, and yes, we do want to use authentication for the invocation. Feel free to tweak variables like timeouts and resource allocations, but we can stick with the defaults and tweak later. While we're partial to Python for our environment, feel free to use this as a sandbox for your own experiments. As for requirements, we'll need the Google Cloud Translate package. In the code, we'll import the translation module here and set up a client. Let's clear out this placeholder text. We'll be getting our SQL data from BigQuery in a digestible JSON format. Further, we'll get this calls key for the records in requests. As for our results, we'll tie them all together and return them to BigQuery. For these remote functions, we need a response following this replies format, so that's precisely what we'll deliver. Now, in our function here, we've drafted out everything that we need. Let's put pedal to the metal and deploy this. With our setup looking shipshape, we'll move along to the networking and permissions. Back in the BigQuery world, we'll build a bridge to this remote function known as a connection. For the connection type, we'll pick the remote functions option and then give this a connection ID. When we leap into this connection in the Explorer, it greets us with the service account ready to be integrated with those remote functions. When adding that service account to the permissions, it looks like the required Cloud Run roles aren't popping up, maybe because we just enabled the API. No worries, let's use the provided helper code. Now we'll paste in the service account and give it the necessary permissions. Once more in the BigQuery realm, we'll create a SQL function that maps to the cloud functions, all in the standard SQL style. The missing link is just the endpoint of our function, conveniently found here. Let's see if our efforts were rewarded. Can we translate those lorem paragraphs? Before testing yourself, be sure to price out the translation work involved here. It's easy to rack up costs if you're doing more than 100 or so translations. As with other services in this video, the Translate API in Google Cloud is not free. Our command seems to be moving quite slowly, an excellent excuse to check out our cloud function for any alarm bells. And there it is. Calls is AWOL. A quick fix and we'll redeploy. The endpoint looks steady, so we can fire up our query in BigQuery again. Some of these larger remote functions can take a while, so let's review the logs to see if everything's smooth sailing. These 60-second timeouts may need some revision, and a bump to memory and CPU couldn't hurt either. Alright, let's release that query once again, now with this review ID filter for a swifter response. Another learning opportunity, it appears we need to grab the translated text, not just the raw response from the Translate API. Alright folks, after a couple of rounds of tweaks and deployments, we have our function operating as expected. But we can't call it a day until we have a heavy-duty large language model in our AI API integrations arsenal, right? So let's dive in and add that as another remote function. We'll set this up so that it can tackle any large language model tasks that you throw at it. Our secret weapon for this task is the Google Cloud AI Platform Library. And no, you don't have to take notes. We've got you covered with copy-pastable code in the video description. We'll use the Vertex AI text generation model system, and for some extra fun, use it with a brand new model. Meet our new friend, the Text Unicorn model. It's a tad more expensive than the default Bison model, but how could we pass up on something named Unicorn? Alright, let's get to it. Overall, the approach is basically the same as before, we're just using a different SDK for a different type of processing task. Let's interweave our translated text and the large language model processing, hopefully unveiling the masterpiece. Quick debugger tip. At any hint of trouble, read the log files like your favorite book. In this case, we seem to have triggered a quota limit for this specific model. Go to Quotas and sort. See, there lies our culprit. We hit the super slow speed limit of 5 requests per minute for this model. Going at this speed for 1,000 records would mean a very long query. The quickest fix? Switch to the text Bison model instead, which has a more generous quota. We've made the all-important tweak and redeployed the function. Fingers crossed as we test our query again. Presto, we've turned random text into product reviews. With that milestone, let's capture our findings before we journey on to entirely new territories of data warehousing with AI. As a reminder, our trusty BigQuery is front and center, while Cloud Functions come to the rescue for a SQL-based Vertex AI and ML APIs integration. Through the power of remote functions, we've created a bridge to specialized AI models and generalized AI large language models. And remember, there's no need to create different large language model functions for different use cases. Let SQL handle all the prompt creation and engineering. Reuse and recycle. Now, on to showcasing our pipelining technologies with tools like PySpark. Modern cloud providers make this sort of AI-based data transformation a breeze. But why just tell when I can show? Let's finish out our functions and then dive in. Oops, we seem to be running into some turbulence again with our LLM. Let's return to Cloud Functions and investigate. Looks like we've triggered the quota limit, even for text Python. We could tweak the max batching rows to say 10 to prevent large batches and keep our functions cruising smoothly with no more than 10 LLM requests at a time. If needed, you could also add static waits in your Python functions using the time module. Okay, now we're cooking. After a few tweaks, our function is looking and working much better. However, even with those smaller batches, we're only going to be able to process roughly 50 requests per minute at best. So, for say 1,000 reviews, we're looking at a waiting time of nearly 20 minutes. So let's just analyze a portion of the reviews, maybe just 100. That should be possible in just a minute or two. Great, we got all the text reviews ready to go. Now, as promised, let's quickly dive into our AI pipelining work. We're going to use the trusty Cloud Shell editor again. As for our PySpark tasks, we'll be creating a serverless pipeline that allows us to extract, AI transform, and load our BigQuery data. Simple, right? We're going to use basic sentiment analysis with regex rather than more complex ML processing and libraries, but the principles are largely the same. We've named this pipeline BigQuery Product Analytics. It's going to check for negative and positive words in the descriptions that we previously created and give us a sentiment score. We'll be using our custom function for sentiment analysis to generate a new sentiment column. That's going to be added to the existing columns and materialized as a new table in our existing dataset. To kickstart this, we'll need a cloud storage bucket to store the PySpark code. Let's build one together, mostly sticking to the default settings. Now, we'll copy our PySpark pipeline specification into that bucket. And now we're ready to run this as a serverless Dataproc job under the Batches section in the Dataproc service. Looks like we need to enable some APIs. We've got a loading error. Let's fix that. Head over to Compute Engine to enable the API. Then we're going to do the same for the Dataproc service. Now we're in a better place to run a serverless task. We'll choose PySpark for the batch type and specify our Python file for the main Python script. It looks like we might have a network not found issue because we haven't set up private Google access, a prerequisite for these serverless PySpark jobs. Let's sort that out by setting up private Google access in US Central. Let's see if that works for our Dataproc now. Okay, things are looking up and we have a valid network and subnet. It's time to run our PySpark job. The default settings should work pretty well. We'll use the default Google Cloud Service account, which should have enough permissions to cover the BigQuery task. Before we move on, let's take a minute to jot down what we've done so far. Remember, we're utilizing the Dataproc service for a managed Apache Spark. As our work grows, we'll be able to do a variety of AI and non-AI work through these Dataproc jobs or integrate with external ML systems. We could even connect to Vertex AI. We would just need to set that up in our PySpark code, somewhat like we did in the remote functions case. Our PySpark task threw up an error, time for a learning opportunity. It couldn't locate the PySpark package. Have we missed something? Let's double check our settings, including the PySpark Python file. All looks good. It should theoretically run. Yikes, it seems our job is still not running. As a common debugging step, we could try a different runtime version. The non-serverless approach by using a static cluster is also sometimes helpful for debugging. Let's go ahead and set that up as an example. It's a pretty straightforward approach. We use just a single master and mostly leave the defaults, except for bringing down the disk size a little bit on our single node. The rest looks pretty good, so let's create this cluster. With the cluster up and running, we can run jobs against it from this Jobs tab here. So let's submit our job to the cluster. Specifically, we have a PySpark type job, and we just need to provide the Python file from our Google Cloud Storage bucket. We don't really need much else here. Let's submit the job as it is and see if it runs successfully. Alright, so there's a bit of a tricky error here. We have a naming collision because the file is named PySpark and the module is also named PySpark. If we rename this to just be pipeline, for example, we should be good. Let's try that again with the serverless data proc service. And with some undeserved confidence that this will run successfully, I'm going to go ahead and tear down our previously created static cluster. Alright, we get an error, but at least it's a different one, which is a victory in my book. Let's revise our script here to have a temporary storage location for that table creation. We're going to need something like this option here, and we'll just specify the existing PySpark bucket. After a successful pipeline run, we'll check our results. So we're creating a table called sentiment. There's our sentiment table, and it looks great. We have some neutral, positive, and negative reviews, a good mix. Having achieved success in our third category of AI integration, let's quickly capture our findings in the notes. The major message here is to keep these Python scripts clean, simple, and minimal. Also, take advantage of the fact that the major cloud providers all offer platforms capable of running these major frameworks, usually in a serverless way. For our next example, we'll look at how to generate SQL for BigQuery. We might have, for example, some natural language prompting that we want to use to generate BigQuery-ready SQL. This will all take place in Vertex AI and specifically the Generative AI Studio. Before we go there, let's just grab our schema. We'll grab all of our text fields here and then copy this as JSON. This is a nice feature to quickly get table context for use in your LLM prompting. Now, in the Generative AI Studio, we'll go to the Language section and then to the Code. We've pasted our schema and are now ready to request SQL from the LLM. While adjusting parameters, it's crucial to monitor the token limit, as it will determine the size of the output. When you expect a larger SQL script output, consider increasing the token limit. The advanced options offer more configurability, but the default settings should suffice for a good result. Let's test this. The mode indicates the most prevalent sentiment, which is what we're analyzing with this query. Since we didn't provide the complete dataset in the prompt, the LLM of course didn't include that, but otherwise this looks good. Upon review, it looks like the most common sentiment is positive, with a count of 64. We've successfully generated usable SQL for BigQuery. To integrate this into a programmatic workflow, like a pipeline or script, use the Get Code button. Next, we'll explore turnkey AI services on top of BigQuery, primarily focusing on Vertex AI. This includes services like Vertex AI Search and Conversation. However, while we're here, let's jot down some notes on our SQL generation in the Generative AI Studio. The key takeaways are to provide ample context and to be mindful of the token limit. Moving along, jump into the Vertex AI Search and Conversation service. The app options showcase functionality like search, chat, and recommendations. These options are all set up similarly, so I'll demonstrate the first one, but remember, other applications are available. We'll be using the data stored in BigQuery, specifically our English reviews table. Generally, the more natural language and complexity in your data, the more value you'll derive from this service. And that's it. We've created an AI-powered app with absolutely no code. For larger tables, it's going to take a while for the content to index, but since we only have 99 documents, the indexing finished very quickly. You can see all the indexed documents here. Now, let's highlight actually searching with an AI-based semantic search across these documents. If we search for reviews that were very bad, we see things like, "I would not recommend this product to anyone," and "this product doesn't work for those suffering from pain." These reviews, of course, don't include terms like very bad directly. Rather, it's doing a semantic search for meaning across these documents and therefore giving you a really nice, flexible way to query your massive data. We'll be releasing another video shortly on quickly building a multi-data source custom search application for your data warehouse, but we'll stick with the basics for this video. As you would probably suspect, there's some nice configuration points for this AI search, as well as ways to easily integrate this with your applications. Of particular note from our experience here, take advantage of cloud services for common AI use cases like search, chat, or recommendations. These are straightforward to set up and are still quite configurable. This video is a part of our AI series where we'll be making a donation of $1 for every 10 subscribers to this video. So if you'd like to support the great folks working on AI safety research, as well as the channel, consider subscribing. Thank you very much for watching, and please enjoy responsibly.